Today I'll be discussing about one of the topics in the AP Statistics exam, which is experimental design. This will cover one of the methods known as SOX, which is the shape, center, spread, and outliers. So what is experimental design? Experimental design is basically describing patterns and departures from patterns. This accounts for 20 to 30% of the AP exam. Um, It is exploratory analysis of data, makes uses of graphical and numerical techniques to study patterns and departures from patterns. Emphasis should be placed on interpreting information from graphical and numerical displays and summaries. So experimental design, one of the methods to describe data and their graph is a method known as SOX. SOX basically stands for shape, that stands for the first S, outliers, which stands for the O, center stands for the C, and spread, which stands for the last S. So experimental design in terms of shape, this is when you describe a distribution shape and concentrate on its main features. This is when you look for rough symmetry or cleared skewness. A distribution is roughly symmetric if the right and left sides of the graph are approximately mirror images of each other. So basically, they should look roughly the same. Doesn't have to be approximately or an exact replica of either side. It just needs to look roughly the same. A distribution is skewed to the right, or known as right skewed, if the right side of the graph is much longer than the left side. This basically means if the right side of the graph has a longer tail, if 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 it has more values on that right side. Same goes when it's skewed to the left or left skewed. If the left side of the graph has much longer side than the right side if it has a longer tail. We can also describe the shape of a graph by how many peaks it can have. Unimodal when it has one peak, or bimodal when it has two peaks. These are examples of shapes, symmetrics. As you can see from this graph, it isn't approximately symmetric, it isn't a exact replica. It's roughly symmetric. I mean, rough estimate that these values on either left or right are close to each other in terms of amount. Skewed left, as you can see here, the left side has a longer tail, and where the peak is at, or I guess the center, you can see over here, it has a longer side over here on the left side. Same goes for this graph. Skewed to right has the longer tail over here, as you can see. Moving on to experimental design and outliers. Basically, an outlier is an observation if it falls more than the 1.5 times inner quartile range when it's above the third quartile or below the first quartile. This is when, if we're looking at a graph, when a point is way off the 1.5 times IQR equation. This is when it's way past than the average numbers we have, or we see in a dot plot, but it's way out in terms of left or right. Remember that the IQR rule is basically the third quartile subtracted from the first quartile. Moving on to experimental design in terms of center, this is when we find the mean in the data. This is the most common measure of center is the average or the mean. When we find mean, we basically take the number of observations and we add up all their values and divide it by the number of the observations. So we basically take all the data, add them all together, and divide it by the amount of data we have. So as you can see from this equation, x bar equals to the number of observation divided by the number of observation over here. You can see x1 plus x2, etc., divided by a number of observations. Moving on to experimental design, spread is refers to the variability of the data. If the observations cover a wider range, then the spread is much larger. Sorry. If the observations are clustered around a single value, then the spread is much smaller. Remember the interquartile range, it's basically a useful numerical description of a distribution which requires both a measure center and a measure spread. Remember the IQR is the third quartile subtracted from the first quartile. To find upper bound in the spread, we basically take the third quartile plus 1.5 multiplied by the IQR. And to find the lower bound, we basically take the first quartile subtracted from 1.5 times the IQR. If we want a quick summary of our data, we basically use a 5-number summary. This consists of the smallest observation, the first quartile, the median, the third quartile, and the largest observation. Right in order from smallest to largest observation. This accounts for minimum, first quartile, median, third quartile, and the maximum point in the data. Continue on to spread. When we want to calculate the quartiles, we arrange the observations in increasing order and locate the median. The first quartile is, or also known as Q1, is basically the median of observations located to the left of the median, and the ordered list is basically how I approach most of these. Is I think of the first quartile, the first quarter of data in the data list. So this is basically the first 25% of the observations. And the same goes for the third quartile. It's basically the median of observations located to the right of the median in the ordered list. I look at it as the 75% of the data in the data list. So I try to sort each data point in the data list by fourths to, by 1/4 each, 1/4 here, 1/4 there, 1/4 there. So basically, I think I approach it as Q3 would be the 75% there, or the 3/4, and the Q1 would be the 25% or the 1/4 in the data list. So we have a sample problem for experimental design, number 37 on page 41 in the textbook for the practice of statistics. Students in a college statistics class responded to a survey designed by their teacher. One of the survey questions was, how much sleep did you get last night? Here are the data in hours. As you can see, we have 28 data in this data set. And the first thing it asks us is to make a data plot to display the data. Well, our data has been made in, so our sample problem back, and our first instruction is to make a dot plot to display the data right here. So we made a dot plot already in here. As you can see, it's a unimodal graph. There's only one hump, one peak over here. Looks roughly symmetric. I think it's skewed to the right. I can see that at least if we cut the data in half, the numbers are very close to each other. And we set the numbers in ascending order. This is where the 14th number is at. So since it's even, what we have to do is we take the two numbers in the center, add them together, and divide by 2. So 6 plus 6.5 is 12.5, divided by 2 is 6.25. So the center is roughly at 6 if we have to round down. And it seems to be no outliers. I mean, we can consider 11 to be an outlier, but if we have to do calculations, but we're just looking at this graph in terms of a 5-number summary, 11 it wouldn't be considered as an outlier. It seems to be close to the center, at least at a reasonable space. So we already did our part A. We already drew our dot plot. Now we just have to do part B, which asks to describe the overall pattern of the distribution and any departures from that pattern. So basically, this is when we do shape, center. This is when we do sucks. So the shape, we can say the dot plot is roughly symmetric. It is a unimodal. I think I spelled that wrong. There's a modal plot is a unimodal graph. Now center. The center is at about 6 hours. 6 plus 6.5 equals 12.5 by 2 is roughly 6.25 hours. We could also say because the highest point there are at 6 hours in the dot plot. Shape center spread. So the spread in the dot plot, we're just using the 5-number summary. We just look at the minimum and the maximum. So the minimum looks to be about 3 hours, and the maximum looks to be at 11 hours. So we can say the spread of the data is between 3 hours, which is the minimum in the data set, and 11 hours, which is the maximum in the data set. And outliers, we already discussed that seems to be no outliers. If we want to remove this, and over here 2 and 12 won't be any outliers. 11 seems to be at a reasonable space from the center. So we can conclude there do not appear to be any outliers, in the distribution. And so that concludes experimental design. We concluded both A and B in number 37, page 41. And that's it for experimental design.